Okay, so this is a theoretical video rather than a question. So this is breaking down the scalar and vector resolute concepts for a pair of vectors. So this is resolving vectors into their parallel and perpendicular components to another vector. So if you notice here, this vector is the vector component of v that is parallel to vector u. So notice we're parallel to vector u here. And this guy here is the vector component of v that is perpendicular to vector u. And what you'll hopefully notice straight away is that the v parallel plus the v perpendicular will always equal that vector v. So traveling along here is the same as traveling along here and then here. Okay, we end up in the same place. But where do we get these vectors? So let's first find what's called the scalar resolute. So we're going to find the scalar resolute. Okay. And the scalar resolute can be written as the magnitude of the component of v that is perpendicular to u. So what we're finding here is the length of this line, for lack of a better word. So we want to find the magnitude of that vector. So we're going to add some information here. So we're going to first notice that this angle here can be called angle theta. And what you'll notice is that the cosine of theta is equal to the magnitude of that v parallel over the magnitude of v. And that comes from the adjacent hypotenuse ratio. Cosine of an angle is the adjacent divided by the hypotenuse. So this lets us say that the magnitude of v parallel is equal to the magnitude of v times the cosine of theta. Now, hopefully, that cosine of theta is giving you an idea of something that we can use. So what we're going to use here is the definition of the dot product. So you should be able to remember that v dot u is equal to the magnitude of v times the magnitude of u times the cosine of that angle. Now this means, by division, that the cosine of the angle is equal to the dot product over the magnitude of v times the magnitude of u. Let's rule that off. So now we can say that the magnitude of v parallel is equal to the magnitude of v times v dot u over magnitude of v, magnitude of u. Now you'll notice these v magnitudes cancel, so we're now able to say that the magnitude of this vector v parallel to u is equal to v dot u over the magnitude of u. Alright, so that's our scalar resolute. Okay, so this is our formula for our scalar resolute, and it gives us the length of this line. Now we want our vector resolute. So let's zoom in here. We actually want this vector. We know its magnitude, so let's write its magnitude here. So let's do a little brace. And its magnitude is v dot u over the magnitude of u. So what we want to do is we want to find a vector that's parallel to u, hence parallel, but is this long. So we want to find a vector that has this magnitude here that points in the same direction as this vector u. So we're going to use the unit vector. So the unit vector in the direction u is denoted as u hat, and it is equal to the vector u divided by the magnitude of vector u. And its magnitude will always be 1. So the magnitude of u hat equals 1 all the time, okay? So we've got now something that has magnitude 1. We know we want to force this magnitude. So if I want to get a vector with this magnitude in the direction of u, I multiply by u hat. So what that lets us say is that the vector component of v, actually let's do this in peach, the vector component of v that is parallel to u is equal to v dot u over the magnitude of u all times u hat. And we can clean this up even further if we wanted to, because we should be able to recognize that u hat is u over magnitude of u. So this becomes v dot u over magnitude of u all multiplied by vector u over magnitude of u. So this is going to let us multiply across here. So we're going to take that down to our next page, and we're going to be able to say that v parallel is equal to v dot u over magnitude of u squared all times u vector. Now, magnitude of u squared, by definition, magnitude of u squared is equal to u vector dot u vector. So we can simplify this even further. V parallel is equal to v dot u over u dot u times u. So that's our definition for v parallel. And we can really tighten it up if we wanted to, because what we've got, if we want to go back the other way, we know that u parallel is equal to v dot u over magnitude of u. So let's go back to this definition. So we can also say that v parallel is equal to v dot u over the magnitude of u, times u hat. But notice what we've got here. This is u hat. If you want to really tighten up this definition, you can write v parallel is equal to v dot u hat times the vector u hat. Okay. So this is the definition that you might want to think about it as. This is easy to remember. And when you're calculating it, I would be inclined to use this vector. So the scalar resolute, this scalar resolute here, can also be written as v dot u hat. Okay, and for my money, that's a really nice way to remember it. And a mnemonic that I often use, the hat goes on the vector that's underneath. So u is kind of wearing v as a hat here. And that helps me remember it. So then I can define v perpendicular. So that's this guy here. And notice v perpendicular will be v minus v parallel, which I can do algebraically. So I can say v perpendicular is v vector minus v parallel. So for calculation, I can write that as v minus v dot u hat times u hat. And that will give me the vector component of v that is perpendicular to u. Okay, so the formulas you want to know how to use this guy for remembering, this guy for calculating, and this one kind of has everything you might need to know in it. But the most important thing to take home from this is how these formulas are derived. So how do we get this vector? We get its magnitude by leveraging our understanding of the cosine, and we get the vector itself by remembering that we want to multiply by 1. So when we're multiplying by 1, we're not changing any length. So we can force this direction to have a particular magnitude. All right, I hope that was useful. Good luck.